is Taran Packer, and I'm a simulation support specialist here at GoEngineer. Today I'd like to talk to you about a support case study that came from a life science company which designs and builds DNA sequencing systems, which is what the device in front of you is meant to do. It is a simplified version of a much larger assembly that the company wants to analyze in linear dynamics. And basically this assembly is made mostly of aluminum with a very complicated lens assembly within it. And what the company wants to do is see how long it takes their assembly to dampen after it's hit with a large acceleration over a very short time period. But they weren't really sure how to go about setting up the study properly to do that. So I showed them some great tips and tricks to help them along their way, and I thought it would be a good idea to show everyone else the same tips and tricks in case you came across a similar situation where you wanted to see how long it takes your designs to stop vibrating after a specific amount of time. So the first thing you want to do before you start any linear dynamic study is to do a regular frequency study. These frequency studies give two main things. They give the natural frequencies of the object, and they also give the mode shapes of those natural frequencies. These mode shapes don't give displacements. They just give relative shapes that the device will be undergoing depending on any given natural frequency. So to see those natural frequencies, you right-click Results, and you go to List Resonant Frequencies. You can see here in this study, we've gotten 10 natural frequencies. So, how that translates into the linear dynamics study is by looking at the list mass participation. So you right-click Results, you click on this mass participation, and now I can see those 10 studies and what mass in each axis contributes to each of these natural frequencies. X direction, I have 81% mass participation. In the Y direction, I have 83% mass participation. And in the Z direction, I have 82% mass participation over these 10 natural frequencies. What that means is in any linear dynamic study, you want at least 80% of the mass participation to be in the linear dynamic study. So if I had one of these columns under 80% mass participation and my shock load or whatever load I'm applying to my linear dynamic study is principally in that particular axis, then I need that axis to be above at least 80%. In this case, all the axes are above 80% at 10 natural frequencies, so I'm not going to need to add any more natural frequencies. If they were below 80%, then I would need to keep on adding natural frequencies until I got them above 80%. So once you have those covered, you know how many frequencies you need to do to get 80% mass participation, you can move on to your linear dynamic study. So I have this study here that I've already run, and in this study, what we did, we came to the study properties, we put our 10 natural frequencies in there, that's all we'll need. And we came to our dynamic options and we just set the time period for 1 second and the time increment for a millisecond, which gives me 100 time steps over that 1 second increment. And then the next thing that we cared about was the mass excitation. So we're applying a base excitation to all the fixtures in this study, and we're applying an acceleration type. We use the right plane as the reference plane, and along plane direction 2, which is straight down in the negative y direction, we applied a 30 millisecond squared acceleration in that direction. Our variation with time curve, if I edit it, you can see the excitation happens around the 22 millisecond mark, and I put a 1 here because that's a factor. 1 times 30 is 30 milliseconds squared at the 22 millisecond time period. And then that lasts until the 34 millisecond time period, and it goes back to 0, and for the rest of the study it's at 0. So if I view that here, you can see I've got the excitation of 30 milliseconds squared, goes to 0, and then there's nothing for the rest of the study. So we want to see what that excitation will do to this device. The last thing is we're looking at dampening. In this case, there is no dampening, and we're comparing it to the next study where there will be dampening. In this study, I have put Raylene dampening, which is the default SOLIDWORKS alpha and beta constants that go into this equation right here, where you have the alpha constant times the mass of the object plus the beta constant times the stiffness of the object. This is a viscous dampening type model. Basically, it's saying that I've put this object into water or some other liquid, and that liquid is what is causing the dampening in this system. Complete Genomics didn't know at this time period exactly how their system will be dampened. They need to research that a little bit more. So because I don't know the actual dampening, that's why I chose to use Raylene dampening, which is the default alpha beta parameters. So after this study has run, we can look at the results, and we care about the displacement. And you can see the displacement happening here. I also included a sensor at the very tip of this object. This is where the displacement is greatest, and we want to see when this very tip part of the object will stop moving. So let me show you how I set that sensor up. I used simulation data. I put it on a displacement data quantity. I did resulting displacement, so that's all three axes movement. If you're interested in the max over the selected entity, then make sure you put it to that, not max model. That does the entire model. Or you can do min over selected entity or average over selected entity. I chose max because we're worried about the worst case scenario, and then I chose data point 1 for that dummy mass object. The last thing is you want to make sure, because this is a transient analysis, meaning it's time-based, make sure this is set to transient, not across all steps. So that does all the time points. And as you can see, if I right-click and go to graph, this is how that excitation affected this model. There was an excitation, and then at about 290 milliseconds, that's when it dampens out and there's no more vibration after that. This is actually too long of a period. They wanted to back it off and have it dampen even quicker. So in your own applications, you're going to have to figure out how long you can take to dampen your vibrations and either change your model geometry, change the type of material you're using, change your kind of dampening you're using. All these different factors can change how long it takes for the system to stop vibrating over a specific time period. And you can go through and test each one of those in SOLIDWORKS Simulation linear dynamics analysis and figure that out for yourself. I wanted to also show you what happened without dampening. You can see up here, if I right-click and graph this transient analysis, there's a lot of vibration after the excitation. It's fairly sinusoidal vibration. And if I animate this object, you can actually see it happening. So there's the shock load, and then it just keeps on vibrating and vibrating and vibrating because there's nothing in the system to dampen the energy and take it away from the object itself. This has been Taran Packer. I hope this video has been helpful.